Math 2414, representing functions as power series, video 3. Second example, sneakier use of geometric series. It's not really that sneaky once you see it. You're like, that wasn't so bad. But it's a move that involves making the structure of your function, which in this case is 1 over x plus 2, have a little bit more resemblance to the structure of the sum of a geometric series. All right, so let's see if we can manipulate, finagle, if you will. Let's see if we can manipulate our given function so that it has a little bit more structural similarity to the sum of a geometric series. The thing on top is just a 1. That's great. It's the denominator we need to focus on. Because in the denominator for the sum of a geometric series, we have 1 minus something that's the ratio. And over here, we don't have 1 minus anything. We've got x plus 2. So the first thing I want to do is fix the fact that the constant is on the right by just reversing the addition problem. That part's pretty trivial. But we have a bigger problem. For the sum of a geometric series, we need it starting off with a 1, and we are currently starting off with a 2. So how are we going to fix that? Well, how can you turn a 2 into a 1? Well, you can either subtract 1 from it, or you can multiply it by 1/2. We're inside of a fraction, and we want to change its look. When you change the look of a fraction, you have 2 options. Multiply both sides of the fraction by the same thing, or divide both sides of the fraction by the same thing. But if we're going to divide, we might as well think about it as multiplying by a reciprocal. So let's really say that we have one move at our disposal to change the look of this fraction, and that's to multiply both sides by whatever we want. Well, what I want is a 1 where the 2 is. So what could I multiply both sides of the fraction by to turn the 2 into a 1? A 1/2. And if we do that, that will put a 1/2 on top. Distribute the 1/2 on the bottom, it will give us 1 plus x over 2. So this looks a little bit more like we want. We want a number over 1 minus something. We have 1 plus something, but we saw how to fix that in the previous video. All we have to do is change the plus to minus a negative. And now we've got the structural components that we need in order to view this as the sum of a geometric series. We've got the fraction, we've got the 1, and we've got the minus. Those are the 3 things that you're really shooting for to manipulate a rational function like this to have the correct form to view it as the sum of a geometric series. So, what is A and what is R? Well, A is represented by the numerator, so A is 1/2. Our ratio is the number subtracted from 1, so our ratio is negative x over 2. And now that we've got the first term in the ratio, we can just substitute those into the sum, into the series form for A over 1 minus R. So let's do that on the next page. We have the sum of n equals 0 to infinity of our first term, which was 1/2, times the ratio, which was negative x over 2, to the nth power, and this will converge when the absolute value of the ratio is less than 1, but the ratio is negative x over 2. All right, so we're going to do the same 2 things that we did before. We're going to manipulate the sum so that it looks a little bit more like a power series. Remember, we're looking for something like some coefficient times x to a power. So we want to get the x with a power and everything else off the x. And we want to solve this guy over here. So let's start by manipulating the series. To manipulate the series, all we have to do is disassemble whatever is raised to a power. Just remember, if you have a product or a quotient, if you have a multiplication problem or a division problem raised to a power, you can give the power to each piece. So we're going to give the power to the negative in the form of a negative 1 to the n, the power to the x, and the power to the 2 on the bottom. Now that we've exposed the x to the n, which is what we're looking for to make this have a more proper power series form, let's see if we can do anything with the rest of the stuff around it. Well, this one over here is going to get multiplied away, so I'm not worried about that. But we have a 2 times 2 to the n, So we can just add their exponents and get n plus 1, the implied power on the first two being a first power. So let's do all that. Sum n equals 0 to infinity. The 1 on top of the 1/2 doesn't matter. We have negative 1 to the nth power. In the denominator, 2 times 2 to the n is 2 to the n plus 1. And we have the x to the n. And now we've got it looking a little bit more like a power series, the sum of a coefficient times x to a power. Now, what about the interval of convergence? Well, let's go back over here. When you have an absolute value with a negative inside, a negative multiplied, if you will, you can ignore it. If you had something like this, you couldn't ignore that negative because you don't know if this is positive or negative. But if you have a negative factor, a negative is a multiplier, if you will, you can ignore it inside of an absolute value. And so we can sandwich x over 2 between negative 1 and 1, solve it by multiplying everything by 2. We get negative 2 is less than x is less than 2. Now you might be wondering what would happen if I did not throw away the negative. Well, we still would have sandwiched this between negative 1 and 1, multiplied everything by 2, but then we would have to divide everything by negative 1 and reverse the order of the signs. And if you notice, we get the exact same thing, just backwards. So even if you didn't throw away the negative, you still should get the same result. I just don't like dividing by a negative in a compound inequality. So our conclusion, therefore, 1 over 2 plus x, it was x plus 2, is equal to the sum of n equals 0 to infinity of negative 1 to the n over 2 to the n plus 1 times x to the n on the interval negative 2 to 2. Is that what it was? Yes, negative 2 to 2. All right, so by manipulating the original function so that it had a more structural similarity to the sum of a geometric series, we could extract the first term, the ratio, and then go from there.